Hey guys, how's it going? Mr. Mitchell here. In this video we're going to kick off the fields part of the electromagnetism topic by looking at Coulomb's inverse square law. So let's get started. Now it starts here by saying that analogous with the gravitational force of attraction between two masses, there is also a force of attraction or repulsion between two charges, known as Coulomb's law. The force of attraction between two charges is given by this expression here. So it's F equals Q1 Q2 over 4 pi epsilon naught r squared, where F is the force of attraction measured in newtons, Q1 and Q2 are the two charges measured in coulombs, epsilon naught is a constant called the permittivity of free space, which has a value of 8.85 times 10 to the minus 12 farads per metre, and you'll find that value on the datasheet, and r is the distance between the charges measured in metres. Now notice that this expression for the force of attraction or repulsion between two charges is an inverse square law. So we've got that the force F is directly proportional to 1 over r squared, which means that as the distance between the two charges increases, the force should drop off quite quickly. Or in other words, as the distance between two charges doubles, the force of attraction or repulsion should quarter. And just to show you a quick simulation to help you visualize this, let's say I have two charges, Q1 and Q2, where charge 1 is minus 4 microcoulombs and charge 2 is plus 8 microcoulombs, and the centres of these charges are separated by a distance of 2 centimetres. Then you'll see that both charges exert the same force in each other, which is around 719 newtons just now. If however I double the distance between these charges, so doubling 2 to 4 centimetres, you'll see that the values of the forces, so the force in Q1 by Q2 and the force in Q2 by Q1 has quartered. And the same should happen if we double the distance again because it's an inverse square law. So if we double 4 to 8 this time, we should see the value quartering again. So we can see that as distance between the charges increases, the force will rapidly decrease. We can also see this in this other simulation here. So if I have two 2 millicoulomb charges and I bring one over here and then the other one near to it, the two charges are positive, so they should both repel each other, so we should have a repulsive force here. And you'll notice the force just now is about 10 newtons, but if I let this go, you'll notice that the force rapidly drops off over here as the distance between the charges increases. Going back to the notes now, there's a top tip here that you can use when you're doing calculations for Coulomb's inverse square law, and it says that it can be useful to remember that 1 over 4 pi epsilon naught is equal to this constant 9 times 10 to the 9 Newton metre squared per Coulomb squared, to speed up calculations involving this equation. I would say however that it's probably safer just to use epsilon naught as is and plug it in with the value from the datasheet, because this way you're not going to make any errors with rounding. Lastly, it says to note that force is a vector quantity. If more than two charges are present, the force on any given charge is the vector sum of all the forces acting on that charge. So it's important that if you see more than two charges in a question, that you deal with force vectors and add vectors nose to tail in order to get resultant force vectors, rather than using scalars, because force is a vector, not a scalar. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.